Here we have OpenStax Chapter 6, number 71. The first part of the problem is similar to what we did in the lecture videos for a card that's turning on a banked uh, road. And then the second part is a little bit different because we do need to include friction. So let's look at Part A. Part A is talking about the ideal speed. And that means what speed should we make this curve at? What speed should we drive at if we do not want to have to rely on static friction? That's going to be like the ideal speed. So I'm going to draw a free body diagram from a head-on view. So this car is coming straight out of the page, and it's going to eventually like turn to the right, but after it comes out of the page. So my positive R direction is going to be going to the right, and my positive Z direction is pointing straight up. In this free body diagram, I kind of drew the ramp. That's not an axis. I'm just showing the direction so that can help me later when I'm trying to figure out what angles my different vectors are making with my R and Z axes. So the forces that I'm going to have gravity pointing straight down, and I have the normal force which is pointing perpendicular to that surface. So I just want to remind you, even though we went over this in the lecture video, I am not going to break up the gravity force into an mg cosine theta going like that and mg sine theta going like that. The reason I'm not going to do that is that that is a useful strategy when this object is going to slide down the incline or up the incline, because then I care about what is the net force along this direction of the incline. And then I can say that that net force along that direction of the incline equals my mass times my acceleration along the direction of the incline. That's useful, again, that we saw in the last few chapters when the object is accelerating up or down the ramp. In this problem, the object is not going to accelerate up or down the ramp. It's going to accelerate in the R direction. Even though it's on an incline, it's still making a circle that is like in the horizontal plane. So it's always pointing, that R direction is always pointing horizontally towards the center of the circle. And as the object makes a circle, we know whenever an object is driving in a circle or moving in a circle, it accelerates in that positive R direction. So because the positive R direction is the direction I'm going to accelerate in, this is the direction that I want to know what my net force is. So I'm going to figure that out by taking my normal force and breaking that into a Z component and an R component. The next tricky thing is that I need to figure out what angle I'm going to use to break this up. So this angle on the ramp here is 15 degrees. That means like if I drew a horizontal line here, this angle would be 15 degrees, which means this angle is 15 degrees, which means this angle is 75 degrees, and this angle up here is 15 degrees. Okay, so if I want the Z component, so that theta is this angle right here. The Z component is adjacent to this angle, so the Z component gets the cosine. And the R component would be here, that's opposite of this angle, so that would get the sine. So when I break this up, I get n times cosine of 15 going up and n times sine of 15 going to the right. Okay. Now that I have my free body diagram, I can look at the net force in the Z direction. In the positive Z direction, I have n times cosine of 15. In the negative Z direction, I have mg. My net force in the Z direction always, always, always equals my mass times my acceleration in the Z direction. We will not be accelerating in that Z direction. So the a sub z is 0, which means the net force in the Z direction has to be equal to 0. And so that would be n cosine of 15 minus mg equals 0, and then here I've solved for n. Let's just leave it like that, and now I can look at my net force in the R direction. In the positive R direction, I have n times sine of 15, and that's it. My net force in the R direction is always, always, always equal to my mass times my acceleration in the R direction, and my acceleration in the R direction is equal to v squared over r. And I'm going to, kind of consider, maybe not the maximum speed, but maybe I should have called this the ideal speed here. So let's just get rid of that little middle part of the equation because that's not interesting. And I can say n times sine of 15 equals mv squared over r. So then what I've done next is taken my normal force, this expression for my normal force, and I've plugged it in here. So instead of n, I wrote mg over cosine of 15. And then here I've plugged in all the numbers that I know. The m's cancel. And so I'll have tangent of 15 times 9.8 equals this v squared over 100 because my radius is 100. And then I get that I should not call this maximum speed. I should call this the ideal speed, is 16.2 meters per second. So all of this is exactly like what we did in the lecture video. Let's look at part B. Part B is new because now we are not going to be driving at that ideal speed. We're going to be driving at a different speed. And this is telling me if the car takes the bank curve at less than the ideal speed, friction is needed to keep it from sliding down toward the inside of the curve. So let's figure out how fast this is in meters per second. If I'm going to plug that into my equation, I need it to be in meters per second anyway. So I'm going to convert 20 kilometers per hour. Here I'm converting between meters and kilometers. Here I'm converting between hours and minutes, and then minutes and seconds. And I get 5.56 meters per second. So that's the speed I'm going to be using here. So that speed is slower than the ideal speed that we just calculated. That means that if there were no friction, the person would slide downwards. So we want to figure out how big does the friction need to be, specifically what's the minimum coefficient of static friction needed in order to stop this object from sliding down the incline while it is making a circle. So my free body diagram is going to be a little different. I'm still going to look at the head-on view. I still am going to start with my normal and my force of gravity, but now there will be static friction, and static friction is going to prevent the car from sliding down the incline. That means the static friction is going to be pushing up the incline. And now I'm still going to do the same thing where I'm going to break my forces into z components. So this force is going to have a component in the positive z direction, and it's going to have a component in the negative r direction. So I need to know, which angle I can figure out in order to know how to break this vector up. So what I would do is look at this angle here, and that's the same angle that's made between the horizontal and the ramp because the force of static friction is in the same direction of the ramp. So this angle here is 15 degrees. That's what we've been calling theta. That means this angle here is theta. And that's the normal way we break up vectors. So my horizontal component is going to get the cosine theta, and my vertical component will get the sine theta. So this is what I've broken up from the previous problem, and now I'm including that I have the static friction force times cosine of 15 going to the left, and I have whatever that force of static friction is times sine of 15 going up. Okay.